Thermodynamics in Biosystem, Module 4, Properties of Pure Substance, Segment 1, Phases of a Pure Substance. With me, Yusuf from School of Life Sciences and Phenology, Institut Teknologi Bandung. In this module, we will discuss phases of a pure substance, phase change processes, property diagrams, property tables, ideal gas equation of state, and last but not least, other equations of state. A substance that has a fixed chemical composition throughout is called a pure substance, such as water, nitrogen, helium, carbon dioxide, and many others. A mixture of various chemical elements or compounds also qualifies as a pure substance as long as the mixture is homogeneous, such as air, because it has a uniform chemical composition. A mixture of two or more phases of a pure substance is still a pure substance as long as the chemical composition of all phases is the same. We all know from experience that substances exist in different phases. At room temperature and pressure, copper is a solid, mercury is a liquid, and nitrogen is a gas. Under different conditions, each may appear in a different phase. Even though there are three principal phases, solid, liquid, and gas, a substance may have several phases within a principal phase, each with a different molecular structure. For example, carbon may exist as graphite or diamond in the solid phase. Helium has two liquid phases. Iron has three solid phases. Ice may exist at 7 different phases at high pressures. A phase is identified as having a distinct molecular arrangement that is homogeneous throughout and separated from the others by easily identifiable boundary surfaces. For example, is the two phases of H2O in ice water. Molecular forces. It is very helpful to have some understanding of the molecular phenomena involved in each phase. Intermolecular bonds are strongest in solids and weakest in gases. This is why molecules in solids are closely packed together, whereas in gases they are separated by relatively large distances. The molecules in a solid are arranged in a three-dimensional pattern that is repeated throughout, as shown in the right figure. Because of the small distances between molecules in a solid, the attractive forces of molecules on each other are large and keep the molecules at fixed positions. Even though the molecules in a solid cannot move relative to each other, they continually oscillate about their equilibrium positions. The velocity of the molecules during these oscillations depends on the temperature. At sufficiently high temperatures, the velocity of the molecules may reach a point where the intermolecular forces are partially overcome and groups of molecules break away, as shown in the bottom figure. This is the beginning of the melting process. The molecular spacing in the liquid phase is not much different from that of the solid phase, except that the molecules are no longer at fixed positions relative to each other and they can rotate and translate freely. In a liquid, the intermolecular forces are weaker relative to solids but still relatively strong compared with gases. The distances between molecules generally experience a slight increase as a solid turns liquid, with water being a notable exception. In the gas phase, the molecules are far apart from each other and the molecular order is non-existent. Gas molecules moved about at random, continually colliding with each other and the walls of the container they are in. Particularly at low densities, the intermolecular forces are very small and collisions are the only mode of interactions between the molecules. Molecules in the gas phase are at a considerably higher energy level than they are in the liquid or solid phases. Therefore, the gas must release a large amount of its energy before it can condense or freeze. In the next segments, we will discuss about phase change processes. Until then, I am Yusuf from Institut Teknologi Bandung.